My name is Marcin. I live in Poland, where I run a software consultancy called Software Mention with my partners. We are around 70 developers right now, and one of the areas we do is multimedia. We did quite a lot of multimedia projects in the past, and we have been using many available open source tools for multimedia handling, but honestly speaking, all of them had their issues. So at some point, we fell in love in Elixir. So we said, okay, guys, that looks like a language that is well suited for such tasks. So we created a framework. The first version was written by myself. Now there is a team. Its size varies, but it's up to 7 people. And we are working on this already for 3 years, and there are some projects in production that are using Membrane. It doesn't mean we don't use any other technologies. We still do projects in other available open source tools for multimedia. It gives us a lot of insight what is done well, what is done wrong, and we try to put all this expertise in Membrane. Today I'm going to bring you a real use case of Membrane. There will be some basics. The talk will not be very deeply technical. I just want to tell you what is the real story behind one of the apps we released recently. It's a publicly available app already. It's an MVP of an app that is I would say it's a Twitch clone. Essentially, you can stream the live video from your phone to multiple viewers, and it's targeted to the fitness industry. So people are streaming how they are making pumps or any other things on the gym. And the whole multimedia part is based on Membrane. And I'm going to make a short intro how it was done and how Membrane was used for it. Let me share my screen, just a second. All right. So this is a short presentation on how we solve this problem. This is the problem. We have an iPhone. The app is now limited to iPhone, but obviously it can be used on multiple platforms. And we have to stream the video and audio from the iPhone to the cloud, and then from the cloud to the multiple viewers, which are also mostly iPhones, but in the future, more platforms has to be supported. Obviously, when you hear many platforms has to be supported, you hear many formats, many transport layers, many everything. So there are a lot of things that can break. But what is important is that there is limited amount of senders and possibly unlimited amount of viewers. So the system has to be designed to scale. There are some solutions that allows you to approach this. For instance, there is GStreamer, which is a well-known open source framework for multimedia streaming. Membrane is heavily inspired by GStreamer. Even some terms are the same, but implementation is very different. GStreamer has certain limitations based on due to his architecture. That we try to overcome in Membrane. Mostly it's about scaling, reliability, and GStreamer is pretty low level, and it's written in C, so it's very hard to extend and it's time consuming to use it. What if, first of all, if we have already an Elixir app? That was the case in our case because the whole backend for the app was written in Phoenix. So it was natural to use Elixir tool for multimedia. We want to leverage the Beam ecosystem. It's important when it comes to reliability. When you do any sort of broadcasting, reliability is a must, is a holy grail of broadcasting. So using a tool that has built-in features for reliability sounds like a good idea. We would like to scale the AL easily because obviously the amount of viewers is possibly unlimited. And we would like to have certain standard way of defining what happens with the stream when it comes from the sender to the viewer. without going too much into low-level stuff. So not necessarily we have to hire super senior developers to be able to develop the app. And obviously we have to react quickly to changes to the app. As I said, the app is currently it's an MVP, so it's very early. The client is seeking for funding, and it seems that it got funded, so it will be developed. And obviously, as you know from your practice, such app tend to develop and evolve very quickly. So it can be the case where we have to rebuild everything related to multimedia if something changes. And what is important, we have to have an insight what is happening with the stream. One of the major limitations in the streamer is that if something goes wrong, it's very hard to debug. Obviously, you can read logs, you can increase the verbosity level, you can go into, and you can spend a lot of time reading it, but it's always post factum. It's always after something has happened. You don't have really easy way to inspect what is happening real time. And as you know, in Beam, we can connect to the virtual machine and inspect its state in real time, which is super useful when it comes to debugging. One of the major problems in streaming is that if something goes wrong and the client or user is pissed off, you cannot really, you can't easily see what happened because everything is happening in real time, and there are many moving parts that can influence the process. So any tool that allows you to inspect this in real time is very useful. And here we get them out of the box. So, and resiliency obviously, if part of the system fails or part of the stream fails, the whole system should remain stable. So again, Beam is cool. So we decided to use Membrane, despite the fact that it's still pretty early product. And a few concepts about Membrane, how it works. The core idea in Membrane is an element. An element is you can think about it as a black box that does something with the stream that goes through it. So for instance, if you have a MP3 file, you have an element called MP3 decoder, and you can put MP3 into it, and out of it comes the decoded audio. And you can have multiple elements. And depending on the function, these elements have different names. If element just outputs the data, it's source. If it only consumes the data, it's sink. And if processes the data, it's filter. In terms of code, it looks more or less like this. If you create a new type of element, you have to use certain module that will and override certain callbacks, and that's it. More info about this is in the guide. I'm not going to go into details today. What is more important for me is to show you the overall idea. So the elements are grouped in pipeline, and pipeline has its children. And elements have something called pads. Pads are pad can output data or can consume data, so they are called output pad or input pad depending on the function. And what is important, the element can contain multiple pads because, for instance, imagine an element that mixes two videos. So it's going to have two input pads and one output pad. Or you might have an element that decodes the video file, and it's going to output the video stream and an audio stream, and sometimes even subtitles stream. So it can has multiple pads, and some of them might be dynamic, so they can appear depending on what was in the file, and so on. This complexity is one of the reasons why we haven't been using GenStage, because it looks similar at the first glance, but if you go into details, you easily see that the GenStage was made for a bit simpler tasks, but the whole idea is quite similar. And you can link the paths together, so the data flows from one element to another. Most elements, there are two types of elements or paths. Some of them push data and some of them pull data. There are, for instance, the example of element that push data, it can be a UDP source, which is going to push the data as soon as the packet arrives. The type of element that can pull data is the file sync, which saves the data to the disk, which is going to ask for more data as soon as the previous write was finished. And the pull elements are sending demands to the previous elements in the pipeline, and they respond with buffers. And buffers are some chunks of data. Additionally, there are some events, for instance, end of stream, start of stream, and many other custom events, which are specific to the element, which are flowing aligned with the buffers. So we can do sorts of signaling. And sometimes the elements are outputting the notifications, which are not aligned with the buffer stream. For instance, if we have an element that is measuring the volume of the audio that is flowing through the filter, we can set it to output the audio level every 100 milliseconds, and it's going to notify it about it, regardless if the data is flowing or not. Obviously, it all depends on the use case. Sometimes you want to, let's say, output the level every 100 frames, and then it's different element. But if you want to have an element that does something, let's say, periodically, that then is going to communicate with the rest of the app over notifications, which are, you can understand them as sort of wrapped messages, which are pretty easy to handle. As you can see on the code, you have just callback, and that's it. And coming back to the app, I would like to discuss is that was the overall architecture, that we have an app that is talking to certain cloud application that was based on Membrane and Phoenix. And we have mobile apps with clients and mobile apps with viewers. And we decided to use RTP, which is pretty standard way of transmitting live video and audio from the sender. And we wanted to deliver it over HLS, which is more or less standard way of delivering live or semi-live stream over HTTP. HTTP is easy to scale. For those of you who do not know the details, RTP is based on UDP, and one of the challenges we had is that we had to use hardware encoder in the phone. So we had to write Objective-C code or Swift code on iOS to access the hardware encoder. First of all, it was about performance. Secondly, it was about licensing, because the open source H.264 encoder is on GPL, so we were not able to use it. And then there's also a case of licensing. So like we had to pay the royalties to certain vendors. So we had to use the hardware encoder on the phone. So we wrote a piece of Objective-C and Swift code that was accessing the hardware encoder, and raw frames that was encoded by the chip on the iPhone. And then we have been encapsulating this over RTP, which is pretty simple. I mean, that it's mostly about adding some headers and putting this into UDP socket. So it's pretty straightforward. I mean, there are some complex things regarding configuring this, the accessing the hardware encoder itself, but the sending part is not that hard. So the sender was accessing the backend over HTTP and saying, "Hey, I would like to stream," and then the backend was saying, "Hey, you are ready. You can stream to this address and this port," and it just started to send the UDP packets with RTP inside. What happens on the other side is very different. HLS is based on TCP. Because it's using HTTP as a transport, and HLS is essentially having a video cut into slices. So if you have a stream of video, it makes a lot of small files, let's say a megabyte or 5 megabytes each, and the browser is fetching or the client is fetching these videos all the time. So it's constantly polling the server, and then it's reassembling the video stream on the client. It adds some latency because obviously these chunks have a few seconds of duration, and you need to buffer a few of them. So it's not really real time, but it has it's easy to deliver because it's just HTTP, and you can put this anywhere, any static storage, and it's going to work. And it's easy to scale. Because you can cache it, or you can use as storage, like we used in this project we use Google Cloud object storage. So the capacity is enormous. But it's very different. What happens on the sender side and what happens on the viewer side is very different. So what Membrane does, it essentially takes the data from the sender and repacks it into a format that is accepted by the viewer. And this is what Membrane is built for. So what is in RTP inside? We have some transport, and this is the whole problem with multimedia. That if you want to do even the simplest thing, you have to already understand a very large stack. You cannot do this. This is not part of IT that you can just jump in and connect some bits together and it's going to magically work, unless you use Membrane, because this is supposed to hide this complexity from you. But RTP inside, for instance, is a network transport, which is UDP. It's a media transport, which is RTP, which is codec, which is inside contains the raw media. And we have actually two streams because video and audio is treated separately. There are some details like SSRC, which is like integer in the identifier of the sender. There are some problems associated with it. For instance, because it uses UDP, the packets might arrive reordered, and there are many things to handle. When it comes to HLS, the transport is TCP. The media transport is HTTP. Then the clients expect to have something called container, which is kind of a wrapper around the media. And then we have codecs, and that's it. So essentially, Membrane converts one to another. And as I mentioned before, the HTTP live streaming is having a playlist. The playlist contains chunks of files, and these files are fetched by the browser or client, and reassembled on the client. So what sort of pipeline we need when it comes to Membrane? These are the elements that have been used in Membrane. So we have sort of UDP source on the left. I'm reading from the left to right. So the data is flowing to the UDP source. And then we have this RTP parser, which understands what happens in these headers of these packets and can extract the metadata. And then because we can get multiple streams to one socket, we have to route it to appropriate process in Elixir. So then we have SSRC router, which does exactly that. So it associates this integer number with the session ID we know in the app, and it forwards it to the appropriate process. Then we have jitter buffers because, and we have two streams. The top is the video, the bottom is the audio. We have jitter buffers, which are handling the fact that packets might happen reordered. Then we have the payloaders, which extract the data, raw data from RTP. Then we have some parsers, which understand what happens in the media, and so on and so on. And then at the right, we put that together into HLS. At some point, we added encapsulation, which means that some of these things are used very frequently in certain combination. So we created something like RTP session bin, and then which handles just this part of the pipeline. And then we said, okay, but this happens very frequently in many projects, so let's encapsulate that in something higher level. And we added something called bins, which essentially they allow to create higher order elements from elements. So all this part of pipeline here is wrapped into one Uber element called bin that does all this, and you can reuse it in your apps. But if you need to do something low level, you can always fall back to using this manually. So in version 5, we added bins, so it becomes something like that, and it looks simpler. And all of the complexity related to RTP is hidden. So even a developer which is not very experienced in networking and stuff like this can probably use it. And the whole idea of Membrane is about this, to hide this complexity behind certain layer of encapsulation and abstraction. So this is how it looked in greater detail. So this previous part of Magic Black Box called Membrane App is here. And in order, it looks like this. Look at the yellow boxes. So first of all, the client says over regular HTTP post request to the Phoenix app that, hey, I would like to stream. Then the app creates a pipeline per streamer, associates ports, generates this SRC identifier and so on, sends back the connection details, and then the RTP stream is being sent to the over UDP to the pipeline. And when the viewer connects, so this is right part and the red boxes, over HTTP, it asks, hey, what are the available streams? The Phoenix app sends back the URLs of the HLS playlists, and they were, in our case, they were located on Google Object Storage. So they are just fetched over HTTP from the storage, and that's it. It works. So important part, as I said, is that the app can evolve, and if you don't have such modular tool, you might get easily stuck. In our case, that was the thumbnail feature. So the client at some point requested, okay, but I would like to make a view in the app that shows the preview of the videos, but I mean the live videos, the videos that are being currently streamed. So we had to add a feature that essentially takes every nth frame from the stream and saves it as JPEG, and this is being sent to the client. So previously it looked like this. After adding this, it looked like this. So we added an element called T, and T is just an element that splits the stream into two. So the bottom part after this T, I cannot show the cursor because of some limitations of Zoom, but if you go from T to the right, you go to the bottom, this part of pipeline is unchanged. We added just the upper part of the pipeline where you have H264 scissors, which is an element that can capture every nth frame from H264 stream. And then we have video JPEG, which is capable of converting the H264 frame into JPEG still frame. And then we have some video to thumbnail that is shrinking it and so on. So as you can see, you can easily add a new feature and a new thing that does something with the stream without rebuilding the rest. So it allows to quickly evolve the app without rewriting the important pieces of functionality. So why I would like to use it? Well, first of all, it's a certain standard way of defining the primitives. If you ever have been programming the low-level multimedia and you are using some existing libraries, I'm talking about codecs, encoders, decoders, whatever, you will see there is no common pattern on how the API are built. Some are thread safe, some are not. Some are context APIs, some are pretty awful. You will see everything. So Membrane is giving you a like uniform layer on top of it. You can use high-level programming language. If you ever tried to build something based on GStreamer or FFmpeg, not being called as a process, but I mean using actually the lib file, which is beneath that, you know how time-consuming it is. And here you can use Elixir, which is very, very, very nice and high level. And you can easily incorporate this with your existing app. So you do not have to create any private APIs to communicate between your multimedia part and your backend, or so you can just call function from one part to another or pass the message or whatever your architecture is. So what next? The next thing we are working on is WebRTC. For these of you who don't know what WebRTC is, it's a standardized way of creating real-time connections and it is implemented in all modern browsers. So if you are using Hangouts or Google Meet or any other app that is using a video conferencing built into the browser, you are using WebRTC beneath. WebRTC is not one thing; it's a composition of many other standards, and RTP we have been using in the app is one of them. So it's more like like 10 other things glued together than something new. But it's first of all, why it's important. First of all, we have native support in all major browsers. So if you want to create an app that wants to, if you want, let's say we add a feature to the app I have been discussing today that allows to stream not only from the phone, but also from the browser. This is the only way. There is no other way to stream from the browser. It's relatively easy to use from iOS and Android. It's secure by default. The all important data is flowing encrypted. It's standards compliant, and it has a lot of nice features built in that normally we have to build from scratch, such as simulcast. Simulcast is a thing that where the sender is sending the stream in multiple resolutions, and the viewer can automatically select or manually can select one of them depending on the quality. And there are many nice features like that in WebRTC. So essentially what we are aiming at is that this pipeline we have is going to become this pipeline. So the only difference will be that we are not going to be sending raw RTP over raw UDP, but we are going to send WebRTC, which can be a stream from the browser. This graph is obviously oversimplified. WebRTC is more complex than this, but this is the idea. So as you can see, you can reuse the same code and add a new client without a lot of effort. So this is the plan for Membrane. This is the biggest milestone we are going to have. So just a second. And what is the status quo? There are many things to implement if you want to have a WebRTC. There are some codecs because there is more than one codecs defined as a standard in WebRTC. There are transport layers. This is signaling, which means how the two peers are going to talk to each other and negotiate the connection, encryption, and many more. When it comes to encryption, for instance, we are limited by Erlang, by the Beam virtual machine, because some things regarding DTLS are not written properly or not implemented yet. So it might happen that we are going to contribute to the Erlang core just to make this available. And we are halfway to go. Some parts of this are already working, but there are still a few months of work ahead of us. But I think it's still possible this year that is going to be available. And if you need some more information, here are the Twitter handles of Elixir, of the company behind Elixir, of Membrane, of company behind Membrane, and there is my Twitter handle. We have a website. There is a guide, which is, I think, pretty straightforward. Discord, where you can talk to the developers directly. Email that is read by me. And I would like to say many thanks to Dominik Stanaszek, who was working on this application, and he made a significant part of this presentation, and the whole Membrane team. Because, as I said at the beginning, I'm rather supervising the team right now than building new versions by myself. So it won't be possible without all these guys that are listed on the website. And thank you very much. I hope that was interesting to you. I'm going to leave the screen for a second if it was shown too short. I think we have a 5 minutes left, so I'm going to switch in a second to the QA. And thank you very much. I hope that was inspiring, at least to some of you.
It was excellent. It was a very insightful presentation, Marcin. Thanks so much. Very good.
Okay, so I'm switching to the QA, right?
We do have some questions indeed. Let's see if we can address them right away. One is here. Is it possible to use membrane together with nerves, for example, to pre-process a picture or video before uploading it to a server?
We never tried, but I see no reason why it should not be possible.
Mm-hmm. Right.
Because okay, some elements in membrane are just wrappers around the C libraries. So because in some cases there is no point to write a certain piece of code in Elixir because of the performance reasons, especially when it comes to encoders and decoders that should be written in something low level, and sometimes due to complexity. So we try to build as much as membrane as an Elixir code, but some parts are in C. So you have to just take a look which element you are going to use, and if it's based on C, you have to check if the underlying library is available and is going to run on nerves, and that's it. And I don't expect any major problems with that, to be honest. And all the rest is written in Elixir, so if you can run Elixir, you can run membrane.
Good. All right. We have time for maybe one more question. Could you go a little bit more into detail about the changes needed for BIM for the encryption?
It wasn't implemented by me, but from what I know from the developer, it was something about missing headers in DTLS handshake. Yeah, so you can, if you need more questions, you can ask on Discord. I think I can briefly answer the third question about the low level and NIFs, because I think it's something that is interesting and.
Can you please read out loud the question first for our audience?
Was there any challenges when writing the framework about dealing with low-level code and NIFs? Do the users of framework need to deal with this? I think I skipped this in this presentation, but I think this is super interesting. We had some issues, so we created a build system that also takes a lot of problems from you. It's also open source, and you can go to Membrane framework organization on GitHub, and there is a project called Unifex and Bundlex. There are two projects. And essentially, the one is a build system that is cross-platform, and it automatically links with libraries underneath, and it handles a lot of stuff that you don't have to write make files anymore, just like this. And the second is a layer that allows you to write a single C code and run it both as NIF and as a port. So and you have to write it once. So I think both projects are super interesting, and they are like subject for a separate talk, but they are both available on our GitHub, and I think one day they can be used in many other projects behind Membrane, beyond Membrane.